Welcome to the Intel Quartus Prime Software Design Series, Timing Analysis, Online Training Part 1, Introduction to Timing Analyzer. My name is Steve. For this course, I'll go over key elements of the Timing Analyzer GUI with emphasis on evaluation of timing reports. Here are the recommended prerequisites for this course. An online training called Timing Analyzer Introduction to Timing Analysis that can be found on the Intel FPGA YouTube channel or on the Intel FPGA Trading website. Knowledge of FPGA architecture and the design flow, and familiarity with the Intel Quartus Prime Pro software. The Timing Analyzer is the timing analysis engine in the Intel Quartus Prime software. Its purpose is to take a look at the design timing constraints and show you the results of the timing-driven place and route engine from Quartus. The Timing Analyzer is built for all levels of experience so that you can run reports using the GUI or create scripts to automate the report generation. Timing Analyzer uses the Synopsys Design Constraint standard with some additional Intel-specific commands added. Using Timing Analyzer is essentially a three-step process. Set a project for timing analysis, compile your design in Quartus where your timing constraints are used, and then evaluate the results. Setting up Timing Analyzer involves making SDC files and adding them to the project. There are additional timing analysis features that you can enable to facilitate its use. The design needs to be fully constrained to guarantee proper functionality when operating in the FPGA. Since the fitter is timing driven, it will take the timing constraints that you have entered and the fitter will place and route the design elements based on these constraints. Any constraints that are not entered or incorrectly entered will cause the fitter to make incorrect optimization choices. Timing Analyzer only analyzes paths of your design that have been constrained. But constraining your entire design is not as difficult of a task as it may sound, as wildcards are supported, allowing you to constrain general sections of your entire design. Also, once you constrain a clock, then the entire clock domain is constrained. A little bit trickier, but still not too difficult, is making sure you enter I/O constraints, and then add any type of timing exceptions. Each of these different types of constraints are explained in parts 3, 4, and 5 of this series of online classes. Creating your SDC files begins with first creating the top-level SDC file so that you can constrain the design clocks, interfaces, and I/O from the FPGA to the outside world. And more constraints to the top-level SDC file as the design matures. Additional SDC files can be added targeting specific modules or entities in your design, and some Intel FPGA IP have their own SDC files that get automatically added to the project when the IP is used. The text editor in Quartus not only supports VHDL and Verilog for syntax highlighting, but it also supports SDC syntax as well. The text editor has all the basic features that you would expect from a text editor, so not only syntax coloring for the SDC keywords, but being able to collapse blocks of code, autocomplete, delimiter matching, access to templates, and insertion of constraints to help you with your SDC in case SDC isn't quite second nature for you. This is how you enter SDC commands through the text editor GUI. There are a variety of constraints that you can enter. In this example, I've selected the create clock SDC command, and as a result, a user-friendly GUI comes up prompting you to fill in the various fields so that you can successfully enter a create clock constraint. Once you select the insert button, the SDC command is entered at the location of your cursor in the SDC file. The templates in the text editor are accessed from the Edit pull-down menu or by selecting the parchment-looking button on the text editor's toolbar. The templates are pre-built code that makes it easy to insert blocks of code into your SDC file. The templates are found in both the SDC commands and the SDC cookbook sections of the language templates. The highlighted example shows how you would create an SDC code for a 2-to-1 clock mux. The language template also features a user template section where you can create your own block of code to save in the user template area. The settings window of the Intel Quartus Prime GUI in the Timing Analyzer section is where you can add SDC files to your project. The files are evaluated in order with the topmost evaluated first and so forth. The order in which they are read can matter in the event of overlapping constraints. Quartus will generate a warning for any duplicate SDC command that covers the same object with the lastmost SDC command overriding what was read in previously. There are additional Timing Analyzer features that you can enable and disable. On the first tab is the Interactive Timing Analysis tab, which enables some default actions that Timing Analyzer takes after completion of events in Quartus. The default Reporting tab directs the Timing Analyzer to report worst-case timing paths per clock domain and analysis. You can add tickle scripts geared toward timing analysis that will run when the timing analysis engine is run. You can also set up mean time between failure for metastability analysis. Now that the SDC file is ready for the project, you can do a full fitter compilation all the way to bitstream generation. You can do an incremental compilation flow as well, where you run only a portion of the fitter process, such as plan, place, or route, so that you can further analyze your design between each stage. Since the fitter is timing driven, most of the timing driven aspects happen during the place, route, and retiming stages, so SDC changes can be made after the plan stage with minimal runtime consequences to the fitter process. There is a section in the compilation process after all the stages of the fitter have completed called Timing Signoff. It is at the completion of this stage that the default Timing Analyzer reports are generated, and those reports are available in the Quartus GUI. You can also open the Timing Analyzer GUI to generate more reports beyond the default to dive deeper into timing analysis. You can also open the Timing Analyzer GUI after a specific fitter stage for more timing analysis on that stage. The list of reports shown here is the default list when the timing sign-off stage in Quartus is complete. Also, reports generated from tickle scripts in the tickle script file setting will be shown here. Any report name that is red in color indicates that there is some error in which to investigate. Most of these errors will be in the form of failing timing paths, but the red in the unconstrained paths report indicates that there are paths in your design that have not been constrained. The reports listed here are not the only reports that Timing Analyzer can create. You can open the Timing Analyzer and generate more reports specific to the area that you're interested in. Let's take another look at the standard reports that are created in the Timing Sign-Off section after compilation. The majority of reports are the standard reports giving you a summary of the variety of timing constraints such as clocks and unconstrained paths. A tool called Design Assistant, which gives recommendations on potential design changes to help with timing closure, also has a section in this folder. The screenshot also shows a custom report generated by a tickle script to report on clock domain crossings. There are reports that get generated by default to summarize if the design is meeting the timing performance you specified in the SDC file. There are a number of reports to consider so that you know what could be causing the unexpected results. I'll go over a number of these different types of reports in the following slides. The summary slack reports are the simplest reports. For the synchronous analysis, there are the setup and hold reports, and for the asynchronous analysis, there are the recovery and removal reports. In these reports, you'll get a line of each clock domain reporting the worst case values. The slack tells you the margin by which the slowest path is either passing or failing, and if there are failing paths, the total negative slack, abbreviated as TNS, is the total value in nanoseconds of all the failing paths. The Fmax clock speed summary report gives you the worst case slack number, but in megahertz units. The hardened IP that are used in the design have their own reports generated because it can become very challenging to generate time reports for these types of resources using the traditional methods. These reports will indicate the success or failure of the timing constraints. For example, the LVDS SERDES IP report gives a value for the RSKM, which is described in the IP's documentation. The DDR reports present an analysis that is very complicated to do without having the specialized report. To set the IP, a lot of parameters must be filled in so that the IP core knows how to communicate with the memory. The time report that gets generated takes all these values into consideration. The SDC File List reports all the SDC files that the fitter has read in. This report is a sanity check to make sure the SDC was used. If the SDC files are not listed here, then you can investigate why a particular file was excluded from the process. The Design Assistant is a useful tool in the Intel Quartus software that checks a list of design rules against your design. The rules are configurable so you can turn on and off any specific rules that you want to check or not check. The Design Assistant detects and helps you resolve design rule violations by providing recommendations for correction and pathways to the violation source. Avoiding design rule violations improves the reliability, timing performance, and logic utilization of your design. When enabled, Design Assistant automatically reports any violations against a standard set of Intel FPGA recommended design guidelines. You can run Design Assistant automatically during compilation and report violations detected throughout the compilation process. So far, we have talked about the reports that are available from the compilation reports in the Quartus GUI. If we want more information, we can do more extensive time reports by opening Timing Analyzer. If you do a full compilation, Timing Analyzer will automatically open at the end of the compilation. If you only do a partial compilation, such as up to the plan stage, then you can open Timing Analyzer on the compiled database and analyze that completed flow. When the Timing Analyzer GUI opens, the timing net list is generated and the SDC files belonging to the project are read in. Now you're ready to generate reports. The Timing Analyzer GUI is made up of different windows called panes. The various panes are the operating conditions, report, tasks, view, and console pane. I'll talk about each one in the following slides. In the operating conditions pane, you select which timing models to use based on the environment in which your FPGA design will be running. Most of the newer FPGAs have 4 to 6 different timing models available. Timing Analyzer will select all operating conditions by default. If you know that you can guarantee that your FPGA will run in only a specific environment, then you can select only that particular timing net list. All of the timing models are available to use after your design has completed the route or finalized stages in the fitter. For example, if you open Timing Analyzer after only the plan stage, then only a subset of the timing models will be available to use. The task pane provides easy access to commonly used operations. Most of the tasks are report generation, but few of the tasks involve initializing Timing Analyzer with the timing netlist and SDC files. When you double-click on a task to run, any dependent command will automatically execute. There are default settings for the projects that you generate in the task pane. If you need something beyond the default, then you can run the same reports from the Reports pull-down menu and then enter the parameters that are of interest to you. A report that you generate during your current session with the Timing Analyzer will show up in the Reports pane. There is a listing of all the reports in this pane, and whenever you generate a new report, that report gets added to this list. Select the report that you want to see, and it will appear in the View pane. Once you have the report to the View pane, you can control its visibility. You can filter in the information so that you have a large report with a lot of results. Instead of regenerating the report to reduce the information, you can just filter for keywords in the report. Another nice feature of reports in the View pane is you can view multiple reports simultaneously. If you click on the plus symbol in the upper right hand corner of the View pane, you can drag that either vertically, horizontally, or diagonally, and you can split the view window into multiple windows. This feature can be extremely useful, particularly if you want to analyze setup and hold timing analysis at the same time, so you can see if your clock period is skewed too much towards hold timing or setup timing. You want the capturing window more in the center and not too much towards the hold or setup. You can show 4 windows at once as shown here. You can even get creative and have 16 different report windows at once. Next is the console pane at the bottom of the Timing Analyzer GUI. This is your message window, so info messages are in green, warning messages in blue, error messages in red. You can also enter tickle and SDC commands in the tickle console instead of entering the timing constraints through the GUI or modifying the SDC files and then having to reread the SDC files into Timing Analyzer. Any commands that you run through the GUI will also show up in the console pane. This is a nice way to start building a script if you're not too familiar with the Timing Analyzer commands. You can run the command in the GUI, copy the results from the console pane, and then paste into a file that you'll save as a script file. The History tab in the console pane shows only the commands that were executed. After the Timing Analyzer opens, you can generate reports in the Tasks pane. If necessary, the Timing Analyzer will run any required pre-steps to accomplish the generation of one of the reports in the Task pane. If you need more visibility into the parameters of the reports, you can generate more customized reports by using the Reports pull-down menu and then entering the values to the variety of parameters to generate your report. The reports in the Task pane are organized into categories. A standard Slack analysis where the Timing Analyzer will generate summaries for every clock domain for setup, hold, recovery, and removal. Datasheet looks at the FPGA as if it were a standalone product, so the time report details the I/O delays. Device-specific reports tells you about hardened resources, which some have very specific numbers to report. Diagnostic reports will detail any constraint issues or potential missing constraints. Custom reports are any reports that you have generated from the Reports pull-down menu in the Timing Analyzer. Be sure to become familiar with the Report Timer report. This report lets you do a detailed slack analysis on individual paths in your design. It will tell you exactly how the Timing Analyzer got the information for that path. If there is a timing failure and you want to know what it is failing, is my data path too long? Are my clock constraints not described as I expected? And so forth. The Report Time report allows you to fill in various parameters to generate the specific report you're interested in. You can run a report on a specific path, on a clock domain, all the paths leaving a clock domain, and so forth. When you generate this report, the default will be able to send the report into the GUI so you can do a graphical analysis of that path or paths, or you can send the report to a text file. You can capture the details of how you generate the report in a tickle file so that you can automate the creation of this report every time you need to compile the design. This is the Report Timing GUI, where you can enter the parameters you want to generate the exact type of report that you need. You can access this GUI in the Task pane or through the Reports pull-down menu in Timing Analyzer. Up towards the top, you can choose the source and destination clock domains in the clock section. From there, you can choose specific nodes in the chosen clock domains if you want to refine your search. Next, you'll need to choose the analysis type if it is going to be setup, hold, recovery, or removal. Next, choose the number of results or paths for your report. You do not want to choose a number too large that you will only need to get an idea of trends of failing paths. Select the detail level, which I'll discuss on the next slide. There is a field where you can specify the name of the reports generated, and finally, the entire tickle command of your choices is generated at the bottom. The report timing detail levels are Summary, which gives a basic slack number for the individual paths, Path, which displays all the detailed information except the Data Path tab displays the clock tree as one line item. Clock and Path displays the same as Path with respect to the clock. And Full, which gives you all the information about the path and the timing, will go through any generated clocks such as clocks on the output of the PLL. The Full Path option is good if you have large clock skews in your design. Here's an example of a summary report. There's one path per row with basic information about that path, which include the source and destination nodes. The source node could be an input port or a register, and the destination node could be an output port or register. Launch and latch clocks, the relationship or difference in time between the launch and latch clocks, which is the amount of time that the data has to arrive from the source node to the destination node. The delay on the data path and operating condition that is the absolute worst case scenario. If you need more detailed understanding of the paths, then the full path report shown here is what you want. When you run the report, this is what you get as a default. At the top is the same information that you would get in the summary report, where each row is a different path. Selecting a path in the summary view will then pull up more information about that path in the various tabs located below. I will discuss some of these tabs on the following slides. The Path Summary tab tells you how the slack numbers were calculated using the data arrival and data required times. Some additional information that gets included with the path analysis, for example, the Path Summary tab shows timing exceptions that were applied to this particular path. This information is helpful to validate whether or not you put a timing exception constraint on that path. Examining a little bit more, the data arrival time subtracted from the data required time gives you the slack value. The Statistics tab breaks the data down further so that you can see even more information as to how the timing analyzer arrived at the numbers reported. In this example, you can see the number of logic levels is 25. Since the slack number for this path was positive, there is not a problem with the number of logic levels, but in other design scenarios, a high number of logic levels can contribute to a path that is failing timing. Looking further on the Statistics tab, you can see the timing numbers as the path goes through the interconnect abbreviated as IC, and the time the data has to go through a logic cell. The TCO number represents the clock to out timing of that particular logic cell. Looking at the percent of total column, you can see that the interconnect is often many times greater than the cell delay. The Data Path tab gives us a little bit more information than the Statistics tab on the previous slide. Here, we can still see the interconnected cell delays, but we get more information associated with these structures. The total time delay is increased by the increment number as the path progresses. The column labeled RF shows the clock edges associated with that cell and can be one of 4 combinations. RR is for rising, RF rising to falling, FR falling to rising, and FF for falling to falling. The fan-out column is handy because we can see if the number of destinations is getting out of control. The location of the element is noted and can be used if Chip Planner is used to help with potential timing problems. The report on the right ties all the numbers together graphically in a timing waveform. You can see the timing waveform, the data arrival and required times, and how they line up together. The green band is good because this means you have a positive timing slack. A negative timing slack would be represented with the red band. You could use a feature called cross-probing to get more information about a particular path. Right-clicking on the node or path in question can allow you to probe that node or path into another tool in the Intel Quartus Prime framework. For example, you'll be able to more easily determine the sources and destinations of that path to help troubleshoot a timing problem. Some other time reports for the task pane include Report All Summaries, which generates a report listing all slack and timing summaries. The report timing tree will create a basic time report in a hierarchical tree-like structure. Report bottlenecks will report on paths based on a bottleneck criteria such as number of fan-in edges, total negative slack, and others. The metastability report will tell you the mean time between failure of the synchronizer circuits that are in your design. The report skew task will generate a report based on all the skew constraints that you have in your design. Report neighbor paths will tell you information about the source and destination paths of the critical paths in the report. There are many more different types of reports that the Timing Analyzer can generate that aren't discussed in this class, but are discussed in the Timing Closure Instructor-led class. There are a couple more Timing Analyzer use cases that I'll cover. These are modifying the project's SDC file to add constraints or fix already entered constraints and directly constraining the design through the Timing Analyzer's console. You should know that the fitter is timing driven, and any SDC file modified or constraint entered in the Timing Analyzer GUI should be reflected in the place and routed design, which means the new constraints need to be kept in the SDC files and the fitter rerun. If you need to modify your SDC file, you need to make sure that after you modify the file that you reset the design before rereading the SDC file. Since the Timing Analyzer already has the timing netlist and SDC commands in memory, if you don't reset your design and only reread the modified SDC file, you'll have new constraints on top of the old constraints, and depending on the type of constraints you have entered will determine if your new constraints will be accepted or ignored because of potential clashes with the constraints that are already in memory. So the process is to modify and save your SDC file, reset the design, and then generate the reports. When you generate your reports, the Timing Analyzer will go through the process of recreating the timing netlist, rereading the SDC file, and overlaying the SDC constraints on top of the timing netlist. Another method is to add new constraints to your Timing Analyzer session. Recall that there is a constraint dialog box in the text editor, There is a similar way to access constraints in Timing Analyzer through Constraints pull-down menu. By using this menu option, you can add new constraints directly to your Timing Analyzer session. You can also enter the SDC constraints in the console pane. When you enter new constraints through one of these methods, Timing Analyzer adds the timing command to your current analysis. This gives you the opportunity to see how well a new constraint will work with the design's current timing netlist. You can also use the remove constraint command to delete a constraint that you have previously entered either through the SDC file or through Timing Analyzer. None of the constraints that you add through Timing Analyzer, either through the console or the constraints pull-down menu, are saved. When you exit, to save these new constraints in the SDC file, you can also use the write SDC file command from the constraints pull-down menu to write out all the constraints that are currently in memory during the Timing Analyzer session. Now that all the new constraints are entered, you will notice that previously generated reports are now yellow, indicating that the reports are out of date. Before regenerating the reports, run the Update Timing Netlist command in the task pane and then regenerate any out-of-date reports. To summarize this online training, I introduced the Timing Analyzer software tool and how to set up, compile, and evaluate your timing results. This concludes part 1 of a 5-part series. I encourage you to check out parts 2 through 5 of this series listed here. There are many ways to get training about Intel FPGAs. You can watch hundreds of videos on our Intel FPGA YouTube channel, register for our e-learning classes on our Intel FPGA training website, or enroll in one of our regularly scheduled instructor-led online classes. Not only do we have quality classes, but they are also free of charge. If you still have questions about our FPGA products, visit our online forums. One more thing. We are always looking for ways to improve our training. Send us an email with your feedback about the course that you attended. My name is Steve, and thank you for listening to this course.